Our next speaker is Eugene Parker, Professor Emeritus at the University of Chicago. He is a pioneer in the study of solar winds. He is an advocate of solar programs, including the Solar Probe mission. And let's give him a warm welcome.
Well, thank you. I appreciate very much the invitation to attend, and this has been a very interesting day so far, and it looks as though it will continue. So thank you very much. I want to talk about the physics of the heliosphere. What do I punch on here to move it along one?
There, right there.
That one. I would like to begin repeating some things you've already heard today, and which seem to bear some importance for what's happening today. As you know, Galileo said you got to look at it and see what it's really doing, and then you think about what it means in terms of mathematical laws and so forth. And as you know, he got into difficulty because that really was the way to do it, and you really are successful when you go that direction. And well, I'm just commenting here that his writings and scientific success posed a threat to some of the traditional verbal logic and analogies of the Aristotelian professors. And I had not appreciated until this morning to what extent Aristotle was considered you might say, a pre-Christian prophet from the way they treated his view of the world. Galileo's trial and conviction and life-term house arrest followed, and it could have been a lot worse had Pope Urban not transmuted his sentence from prison to his house. Unfortunately, human nature is the basic invariant of human history, and while these days you don't get put in prison, you can pretty well suffer other kinds of difficulties. There are modern parallels which are worth mentioning, and so that we don't repeat them. Of course, it doesn't always work that way. The spirit of the Aristotelian professors and the Inquisition lives on today by some of the referees that I'm sure you have all encountered who will dismiss a paper. Well, evidently they think you're trespassing on their turf, and the vaguest criticism will induce them to recommend that the paper not be published. Editors have a serious problem here, which I think they don't always deal with adequately, but I don't have time to expound on that at any length. The Aristotelian Logic, which is something that you and I do every day dealing with life's simple complexities, you think you compare one thing with another, is an essential part of our life. But on the other hand, when you're dealing with phenomena described by the basic laws of physics, it is not adequate. You have to turn your attention to the basic laws and see to it that you do it right. And appealing analogies are simply not sufficient. Unfortunately, in parts of space science, the Aristotelian verbal logic of analyses has led some to the view that the magnetic fields are caused by currents and driven by currents, and the currents are driven by electric fields. That's the way you might think in the laboratory. You imply an EMF, a voltage across the end of a coil of wire, and you create a magnetic field. There's no question about it. And this is sometimes called the EJ paradigm. If you turn to Maxwell's equations and Newton's equations, you find that they are not expressible in any useful form in the general case in terms of E and J. The shoe just does not fit. What you realize, of course, is that this is an extension of the way we all learned about electric currents and magnetic fields in the laboratory when we were students, young people so many years ago. And somehow there is a reluctance to change the paradigm. Further analogies has led to the idea that, in fact, an electric circuit analog exists which precisely correctly gives you the dynamics of J. And, of course, it makes life much easier. You deal with an ordinary differential equation instead of partial differential equations. And then it is imagined that the electric field in a plasma moving with velocity v given by E is minus V cross B over C. That somehow works the other way around, and the electric field drives the velocity. We could take a few minutes and go through this step by step, but again, I don't think time allows. Unfortunately, these notions are all contradicted by the basic laws of physics. For instance, the electric field, whose stresses are proportional to E squared, is small compared to the magnetic stresses by a factor of V over C squared. It's small on the same level as Lorentz contraction and time dilatation, which of course we neglect. Well, I would not mention this were it not for the fact that the people who use the EJ paradigm have become rather outspoken in the last few years, urging those of us in solar and heliospheric physics to take up their errant ways. And I think one should point out that no thanks, but no thanks. We have our own way of doing things. Our own way of doing things is to use the magnetic field B and the bulk plasma velocity V, when you're talking about the swirling of magnetic fields and plasma, which we would call the BV paradigm. And that gives you what's called magnetohydrodynamics, and that's a simple interaction in which the magnetic field is carried bodily with the fluid. If the fluid flows in a certain way, you can easily sketch in how the magnetic field lines are deformed. Remember, the magnetic field line is merely a geometrical construction to display the form of the field. I once wrote a paper at the request of some physics teachers on the interesting aspects of magnetic field lines and sent it into the American Journal of Physics for publication, which is their journal. And the referee turned it down out of hand because he said only a fool would think that magnetic fields are composed of strings. So, you can't win. Now, this can be, what I'm saying here can be derived formally. The magnetic field moves bodily with the fluid. You use the expression E is minus V cross B over C, compute the Poynting vector, which is the electromagnetic energy flux, and it says the energy flux is simply the enthalpy of the magnetic field, that would be B squared over 4 pi, conveyed bodily with the velocity of the plasma. I don't know, I can't think of a more direct way of doing it, and the essential point is that this magnetohydrodynamics is a mechanical problem where the plasma works against the stresses in the magnetic field. If you have a field like this and you move it like that in the plasma, you're stretching the field, you're increasing the energy of the field. On the other hand, if the field is pulling hard and pushing the plasma, the reverse works. The field is doing work on the plasma. It's a mechanical interaction. You don't need to worry about E and J. They're all there. Maxwell has taken care of them. They're entirely passive. And we'll keep this in mind then as we progress in talking about the heliosphere, which is an excellent example of how the magnetic field is transported bodily in the fluid. We use MHD for understanding the dynamics of the sun, both at the sun and out in the heliosphere. Unfortunately, the magnetospheric physics community and the ionospheric physics community are completely taken over by the EJ paradigm, and it has long since been at a point where at least a young unknown person cannot publish a paper on magnetospheric physics or ionospheric physics unless he uses the EJ paradigm. And the problem with the EJ paradigm is, as I mentioned earlier, the basic equations of physics are not expressible in any useful form, so they turn to fantasy instead. I listed some of the fantasies, and it's an unfortunate state of affairs. I expect it's quite durable, and I'm just throwing this out for whatever it's worth so you can be aware of the problem. So, the heliosphere, that's what I was commissioned to talk on here. And the heliosphere is created by the continual expansion of the million-degree solar corona, which provides the supersonic solar wind. So just think of a wind blowing outward from the sun in all directions, radially, of course. And it moves out farther and farther into space, spreading out as it goes. The density falls off like 1 over r squared. And eventually the wind gets so tenuous that it can't push the interstellar magnetic field and wind back out of the way, and so there's a sort of a balance, and since the wind is supersonic, you get a termination shock, and so forth and so forth. I'll say a few more words about that later. The expanding corona stretches the magnetic field out with it, of course, as I have just explained. So at first thought you'd say, well, there's a radial field everywhere out through space, all the way out to about 100 AU. Voyager 1 encountered the termination shock at 94 AU. Forgive me if I sometimes use the round number of 100. I'm a theoretician, and numbers are rather difficult sometimes, so I use round ones. And let's ask, how does this whole thing get started then, back at the sun? Let's go back to the sun. Obviously, it's the energy from the thermonuclear core of the sun that drives convection in the outer 30% or 2/7 of the solar radius. But let's talk just a little bit about the sun. The standard textbook descriptions of the interior of the sun are correct, but somehow they leave out some of the more interesting concepts. The temperature at the center of the sun is about 15 million degrees. The density is estimated at about 115 times the density of water. It's gas, of course, because the particles don't stick to each other in any way. And at 15 million degrees, that is 3,000 times hotter than the visible surface of the sun, which I'm again approximating as 6,000 degrees. And, 3,000, that's a comprehensible number, but it's fairly large. But the intensity of the radiation from anything at a given temperature goes as the fourth power of the temperature. And if you take the fourth power of 3,000, you get something of the order of 40 trillion. So the intensity of radiation in the center of the sun is 40 trillion times more intense than what you see coming from the surface of the sun. The picture of the sun that this gives you then is that the sun is really mainly an opaque shroud enclosing this fireball, insulating it from space. That's why it's able to get so hot and generate thermonuclear energy. And the shroud is extremely opaque. Energy liberated at the center of the sun takes something like 1 million years to work its way out to the visible surface and be radiated off into space. And we have to appreciate that what we see, even though it may dazzle our eyes, which is a statement about our eyes, really, the sun is a dark shroud, a dark cloak, which preserves the temperature and the radiation from the central part of the sun. It's in that outflow of energy from the core where things begin to get interesting. It's radiative transfer. The radiation bounces back and forth and gradually works its way out through this opaque shroud. But when it gets 70% of the way out from the center, that is about 5/7 of the way, the temperature has fallen to 2 million degrees. That's a fairly respectable number, but even so, the radiation intensity is no longer sufficient to transport all the heat flow out from the center of the sun. So it's a very simple effect then. The central part heats up a bit until it gets hot enough that at 70% of the way out, the gas begins to heat up enough that it's lighter than the gas overhead, and it begins to overturn. And of course, if some gas is rising, it forces other gas, cooler gas, to go back down and be heated, and the heat transport is gradually transferred over to convection from radiation. So when you start at the 5/7 radius, it's a little bit of convection, and as you go out farther, it's more and more convection until you arrive at the surface of the sun, where the heat is mostly transported by convective overturning. Well, that's a slightly different emphasis on the interior of the sun than you normally get, but let's just mention a few things that happen in that convective zone, because they're essential for what happens farther out. First of all, the convection generates low-frequency sound waves. The sun is just a big echo chamber full of sound waves bouncing back and forth. The surface is a reflecting surface because the density drops so precipitously. And you get, I like to call them echo modes, hundreds of them, typical period is 5 minutes, but that ranges all the way from a few seconds to an hour or so for the longer ones. These modes penetrate various depths into the sun, and you can put them all together, and with a lot of arithmetic and the help of a computer, you can work backwards from the known periods and scales. You can work backwards and construct the speed of sound as a function of radius throughout the sun. That's very important because it verifies that the standard model of the sun, based on the assumption that the composition of the interior is the same as we see at the surface, apart from a little evolution. It verifies that particular assumption. After all, you know, it isn't absolutely necessary that the interior of the sun be made of the same stuff as what we see at the surface. It would be nice if it were, and it turned out to be nice. It is the same. It also gives you a picture of the rotation of the interior of the sun. The sun rotates every 25 days at the surface at the equator, and more slowly at the poles, typically 10 to the 32 days. And one assumes that this rates of rotation might extend on cylinders all the way through the sun. That's what hydrodynamics would lead you to believe. As it turns out, the frequencies of these echo modes are split between east and west moving waves. They experience different Coriolis forces, and so they have slightly different frequencies, and you can reconstruct the irregular or non-uniform rotation of the interior of the sun. And I won't try to describe it all, but it ain't like what you thought it was. And a lot of people have worked very hard. A lot of people who are experienced in hydrodynamics have worked very long and hard and have been simply unable to come close to duplicating it. It does not rotate on cylinders. It's a shell with the interior radiative zone rotating more or less rigidly, and then bands of non-uniform rotation at the surface. So there's one very interesting unsolved problem, and I don't know what the resolution of it is. We were talking about it at lunch today. Now, so far as the activity of the sun is concerned, the turbulent convection twists and stretches the magnetic field in complicated ways. The basic idea is that if the sun rotates non-uniformly, with the angular velocity a function of latitude, any north-south field is soon distorted, gets stretched out. That gives you, besides preserving the north-south component, it adds an azimuthal east-west component. And the convection coming up through this east-west component raises up field lines like this, but since it's on a rotating planet or a rotating object, there's a Coriolis force which rotates them, and you get a projection of field onto meridional planes. And the combination of these two effects can be shown rather simply to give you a migratory magnetic field that migrates from the middle latitudes toward the equator. And we, looking at the surface of the sun, see magnetic debris continually coming up in a band that does exactly that, with a half period of 11 years. And so that much of it seems to check. Again, I don't have time to go into it, but there are some very serious unanswered questions which are not popular. That is the diffusion and dissipation required to make this dynamo work is normally attributed to turbulent diffusion. You can imagine mixing up the field, making it diffuse. But there is no theory for turbulent diffusion. You immediately run into difficulties if you try to construct one, and I don't know what the answer is, so I won't burden you explaining the problem. Now, an important part of the magnetic fields is that they are buoyant. They represent pressure with very little mass. And so a region of magnetic field has slightly less gas density in it, and all this stuff tends to come up to the surface then. And really all we know about the fields below the surface is by looking at the debris that comes to the surface and then trying to project backwards. I don't know that we're getting any wrong answers. On the other hand, I sometimes think there's some serious things missing, so we may be doing that. The magnetic stresses, the Maxwell stresses, so to speak, are of a peculiar nature. They seem simple enough. There is tension along a field, b squared over 4 pi, and there's an isotropic pressure in all three directions, b squared over 8 pi. And while this looks innocent enough, you will find that if you have a field with untidy topology, that is where the field is mixed and wrapped in some way, there are no continuous static equilibrium solutions. The only solutions that exist for an untidy topology have singularities in them. That is to say, tangential discontinuities, where a region of field in this direction presses against another region of field in some other direction, and if you let the system relax to equilibrium, it will grow these discontinuities, and of course the discontinuity is another word for a current sheet, and somewhere before you get to the true mathematical singularity, the currents become so intense that they begin to dissipate the field rapidly. That is basically the idea behind the flaring phenomena that you see all over the sun. You see explosive bursts of heat release at the expense of magnetic field, and these flares occur on very large sizes, 10 to the 32 ergs maybe in a half an hour, on down to the little microflares that occur all over the surface of the sun, where the little small fields keep coming to the surface. And Katsukawa and Tsuneda, analyzing the statistical fluctuations in the individual pixels of the Yoko X-ray telescope, even suggest they go down to picoflares. That would be 10 to the 20th ergs. The point is, there is an entire range of flaring on all scales, and this is important for our story about the heliosphere, because plasma waves from the incessant microflares are believed to be the major heat source creating the million-degree corona. So here we are back with the corona again, and that is the origin of the of the heliosphere. But let's pause for just a moment and see if we can understand the solar wind, the supersonic expansion. The gas is strongly bound by gravity in the corona, even at 1 million or 2 degrees. The binding energy is typically 5 times or 10 times the thermal energy, and the gas cannot escape. The part of the corona that you see when you look at the sun is very, very nearly static. It's in the equilibrium is essentially a static equilibrium. But if the corona extends far out into space and the temperature is maintained, as it is by thermal conductivity and probably by active heating too, the gravitational binding energy is falling off like 1 over r, and at typically 5 solar radii, you've gotten to the point where the binding energy has weakened and the continually hot corona now has enough energy to escape to infinity, and since the heat continues to be supplied to the corona, that velocity soon becomes supersonic relative to the temperature back near the sun. That's why you have the solar wind at supersonic speeds. Now, the solar wind, as I mentioned before, pushes back the interstellar gas and magnetic field to about 100 astronomical units. And let's think about how far that is. What do we have to compare with it? Well, Neptune is at 30 astronomical units, and the termination shock is at 94 or 100. Voyager traveled for, I guess it was 28 years before it reached the terminal shock. It's a long walk out to there. Light travel time is 13 hours. If you sent a radio message to Voyager 1 at the time it crossed the termination shock and requested a reply, you would get that message back 26 hours later, the following day, 2 hours later during the day. The solar wind travels out to 94 astronomical units in about a year. A lot faster, of course, than Voyager was traveling, nowhere near as fast as light. So this radial field that's stretched out from the sun by the expanding wind, in fact, is not radial. The radial component is always there, because in the year that it takes to get out to the termination shock, the sun has revolved 14 times, and these field lines remain permanently connected, more or less, and so the field winds around 14 times on its way out to the terminal shock. If you compute the length of that field, it gets to be pretty long. The nearest star, take Alpha Centauri or Proxima Centauri or whatever your favorite near star is, it's about 3,000 times farther away than the termination shock. Voyager 1 would take 75,000 years approximately to go out to that distance if it continued at its present speed, which it surely would, of course. You can see then that solar wind spheres occupy only a very small fraction of space, 3 times 10 to the minus 11 if the solar wind is typical. And the sun at that distance is hardly more than 1/10,000th. The sunshine is hardly more than 1/10,000th as bright as it is here at the orbit of Earth. The sun is a little disk over there, 20 seconds of arc across. So I think you get the picture. It's permanently nighttime out there from our point of view. So it's a sizable thing from our point of view, but small compared to interstellar distances and stellar distances. I should mention in the minute or two that remains that the heliosphere has not always been in its present state. The sun, in its 4.6 times 10 to the 9 years of life, has wandered off through the galaxy, encountering a number of external interstellar conditions. Things have probably been less tenuous and certainly at times more denser than they are now. The present density in the interstellar wind that blows against the heliosphere is about 0.2 neutral hydrogens per cubic centimeter and 0.1 ion or proton per cubic centimeter. You can imagine a case where the infalling neutral, well, let me not get onto that for just a moment. You can imagine if the sun did the improbable thing of wandering into one of these cold, dense molecular interstellar clouds where the density is not 0.2 but 10 to the 5 neutral atoms, it could very well push the heliosphere clear into the orbit of Earth. It's interesting to complicate, very complicated and very academic, I guess I would say at this point. But that kind of thing, or some, perhaps not quite to that degree, has certainly happened in the past and would be particularly interesting, except it will be at another time and no way of investigating it. The infalling neutral atoms are a very interesting and important phenomenon, even in their present tenuous 0.2 per cubic centimeter. They fall freely through magnetic fields. They don't have any charge. They fall in toward the sun under the gravitational field. They're ionized. They are picked up in the wind, which leaves them fairly hot because suddenly their charge is switched on and they're grabbed up in the magnetic field and they swing around the magnetic field then with the velocity of the wind. It is believed that they are accelerated in that termination shock and become the anomalous cosmic rays observed here in the inner solar system. But Voyager 1 and 2 crossed the termination shock and found no evidence for that acceleration. Schwadron and McComas have pointed out that, the Voyager 1 and 2 went through the nose of the heliosphere. The most efficient acceleration region would be the flanks. Maybe they just were looking in the wrong place. So that question remains up in the air. I think I will mention just one last thing then. Our time is pretty well out. We normally draw the shape of the heliosphere as I have shown in the left-hand picture here. Just think of a comet-shaped body attached to this on the right. And that's entirely plausible, created by the impact of the interstellar wind. But very recently, Tom Cremigis, George Gleckler, and a number of other authors have pointed out that the evidence is that there's also some evidence that it doesn't quite work that way, that the impact of the wind is not as strong as the pressure of the galactic magnetic field. And if I neglect the pressure of the wind and draw just the effect of the galactic magnetic field, you get this particular picture over here. Since the wind is not zero, this would not be symmetrical the way I've drawn it here, but their paper is supposed to come out in Science fairly soon now, and that's another interesting question and puzzle that we have. Well, I think that's my time is up. I'll quit at that point. Thank you very much for your attention.
There is time for only a quick question. There is one. Please.
This isn't a quick question, forgive me, and I'll speak with you later, but I was wondering if you would be able to weave into that narrative coronal mass ejections in solar events.
Well, the coronal mass ejection apparently is a magnetic ejection. You accumulate helicity or torsion in the field, and you cross some critical point where the forces go out of balance and it springs outward, and then you presumably rapid reconnection. I mentioned pressing fields together, giving you high dissipation rates. That must somehow free the coronal mass ejection from the sun, essentially cutting off the umbilical there. And there are various views of exactly how it works, and I am not in a position to give you a judgment as to which ones I think are right. There may be more than one kind of coronal mass ejection in the first place. So you have just emptied my memory bank on the coronal mass ejection. I mean, they're fascinating things, but I'm sort of waiting to see until something gets to be definitive.
Thank you, Professor Parker, again.